everyone, my name is Julia Pimentel, and we are the Antistatic Paint System Project Team under the Manufacturing Engineering Education Program MEEP, led by Dr. Bradley Davis. The primary research question we wanted to address and answer was, how do you increase dispersion of carbon fibers in antistatic paint? Now, to provide some context, antistatic paint is commonly used as a top coating on high-speed aircraft for the purpose of dissipating static charge buildup on the surface. These paint systems can be comprised of fluoroelastomer paint and discontinuous pan-carbon fibers. Now, the main problem with such paint systems is the tendency for the carbon fibers to agglomerate and cause paint clumps. This results in either failure to pass the pilot's visual inspection or failure in electrical resistance testing. The ideal mixture ratio for the antistatic paint is 1 prescribed portion of carbon fibers to 1 quart of fluoroelastomer paint. And our primary motivation is to develop methodologies to increase carbon fiber dispersion, reduce the amount of clumps, and therefore pass visual inspection, as well as achieve the target electrical resistance specifications.
Hello, everyone. My name is Matthew Morris. Understanding particle dispersion in different mediums can offer significant enhancements to that system's mechanical, chemical, and electrical performance. The specific research objectives governing our project can be summarized as follows. First, we're interested in exploring methods that can be used to increase the dispersion of chopped carbon fibers in a fluoroelastomer paint system. We hope to eliminate agglomeration of chopped carbon fibers for a more homogeneous application to a surface using mechanical techniques and chemical dispersants. By improving the dispersion of chopped carbon fibers in the paint system across our desired surface, we hope to improve that electrostatic discharge performance of that surface.
Hi everyone, I'm Laura Dawson. As Matt touched on, for antistatic paint, we want fibers of small links that are chopped to enhance the dispersion within the paint and create many connections and pathways that allow the electricity to flow, therefore dissipating the static buildup. First, we wanted to characterize the chopped fibers in order to get more information about them and how this may affect their behavior in the paint. When we first received them, they appeared as they do in Figure 1. They were in small balls that required force to break them apart. Once we got them apart using tweezers, we obtained quantitative values about their dimensions using an optical microscope. In Figures 2 through 5, the fibers are shown at the lowest and highest magnifications achievable on the optical microscope we were working with. We found that their estimated lengths varied from about 102 to 1,682 microns. The fiber diameters were consistent across the fibers and were measured to be about 0.7 to 0.8 microns. These could be reasonably considered to be 1 micron in most instances. The aspect ratios range from about 140 to 2,240 based on the average of the measured diameters.
Hi, my name is Gabriel and I'll be talking about dispersions. As highlighted above, a central component of the project was limiting the agglomerations of carbon fibers that formed in the paint system during mixing. We believe these clumps formed because of the frictional and static attractive forces which carbon fibers have with one another. So our approach, in order to lower these attractive forces, was to employ several chemical dispersants. The chosen chemical dispersants were intended to hydrate and coat the fibers, reducing their ability to attract one another. Although there is not a great deal of literature about many dispersants' relevant interactions with carbon fibers, several were identified. First, we chose sodium dodecyl sulfate, an ionic surfactant quite common but used mostly to separate carbon nanotubes. Secondly, we chose hydroxypropyl cellulose, a relatively uncommon non-ionic dispersant but of a chemical family that has seen fairly extensive use with larger carbon fibers. Finally, we used triethyl phosphate, a strong surfactant that was shown to disperse fibers very similar in size to ours, of about 1.5 to 4 millimeters. In addition to simply mixing dispersants in with the paint system, the fibers were also cleaned beforehand through a soaking and drying process in ethanol and acetate. While there is some knowledge of the abilities of these dispersants to separate various forms of carbon and water, there is almost no research regarding the use of these chemicals in the paint system.
After characterizing the given materials and identifying several dispersants to assess their efficacy in a paint system, our team developed a series of experimental procedures based on relevant literature. Firstly, the fibers were cleaned to remove any surface impurities by soaking the fibers in both acetone and ethanol for a comparative study. After the fibers were soaked for about 20 minutes, they were placed in an elevated temperature environment to remove any excess moisture. The next step was the development of the actual paint system and samples by combining fibers, dispersants, and fluoroelastomer paint at varying ratios. Specifically, we wanted to evaluate different volume percentages of dispersant, And so we used 10 volume percent and 20 volume percent of each of the 3 dispersants. The final paint samples were rolled on a roller at 200 RPM overnight to fully incorporate the fibers in the paint. And lastly, for the application process, the paint was hand rolled onto plastic sheets in 6 by 6 inch squares for electrical resistance testing. But before manufacturing the paint samples, our team wanted to conduct a preliminary study to determine the initial interactions between the fiber clumps and the dispersants, as well as the cleaning solutions. After dropping fiber clumps in solutions of deionized water, acetone, ethanol, and all 3 dispersants, we observed dispersion at time equals 0 and after time equals 10 seconds and 1 minute of stirring. On the left is a table of the results of the solution interaction study. It's evident in all samples that increased durations of mixing yields increased dispersion. In the study, dispersion was measured visually by observing how many clumps are present in each sample. Ethanol, SDS, TP, and HPC had the highest dispersion of carbon fibers. This gave us some insight into how the fibers would react within the anti-static paint system.
Once we combined these elements into the paint, we hand rolled the samples onto the plastic sheet. Upon opening containers, we found that the SDS and the HPC yielded premature hardening of the fluoroelastomer paint. A hardened film of the paint covered the sides and the top of the container, and a byproduct of a yellow liquid was also present. When removing the hardened paint, it came out as rubber-like chunks. The TP and control yielded results closer to what we had originally expected. They formed highly viscous paint that, though was fairly homogeneous, was difficult to roll into the plastic sheet. The TP paints with a 20% concentration of the dispersion rolled on the smoothest. As you can also see, the control paint with a higher paint to fiber ratio, the 27 milliliter sample, performed better when rolled than the control with a lower ratio. A common trend seen amongst all the paints, however, was that they dried quickly and became tacky when doing so, making them non-preferable for rolling. It is to be considered, though, that they may perform differently when sprayed in future testing.
Hi everyone, I'm Kaley Folks, and the first section of the work for the future will be conducting electrical testing. This testing will be performed using equipment provided by a local defense company, Nanosonic. The primary region of electrical testing is to quantitatively measure the dispersion of paint samples. Previous testing has been largely qualitative, and this next phase of electrical testing will give us the opportunity to get solidified numerical results to draw comparisons from. Specifically, electrical testing will be performed on the control samples and the TP-based samples because the other samples were hardened before painting could commence.
As far as more future work we may perform, we may incorporate electrical coils because we believe the fibers group largely because of their electrical charges. So using coils favorably to alter the charges of the mixing system may help with dispersion. Another item is that we may alter the dispersion ratios. Because of the lack of research regarding the dispersants that we have employed in any similar systems, it may be beneficial to alter the amount of dispersant we use. We may implement optical methods to test for effectiveness. Although we will be using electrical analysis to document the successfulness of our dispersions, it may prove advantageous to have another option. And we may also change the mechanical mixing element of the paint system. The current mixing element employs shaking, which may not be forceful enough to fully disperse the fibers, so we may switch to high shear impellers.
And finally, in actual application, the paint system is applied using a handheld spray gun. We hope to develop a similar spray mechanism so that we can compare the differences between hand rolling and spray gun application on fiber agglomeration. We'd like to thank Dr. Bradley Davis, Dr. Michael Bortner, Martin Entomati, and Dr. Thomas Staley, as well as Nanosonic for all their support in completing this project. Thank you very much.